Next, we will discuss how to do calculus with the arcsecant of x function. Let's consider the arcsecant of x function and let's find its derivative. Of course, we can use the limit definition of the derivative, however, we get stuck quick. So let's try the implicit differentiation instead. First, let's apply the secant of x function to both sides, and then differentiate each side. On the left side, we use the chain rule, and on the right side, it is just the derivative of x. Let's divide both sides by secant y tangent y, and replace y with the arcsecant of x. We definitely learned how to simplify such expression in trigonometry. So let's simplify this expression using the procedure developed in trigonometry. First, we introduce theta by labeling everything inside the parentheses as theta. The original expression is now very simple in terms of theta. But what do we know about theta? From its definition, we know the domain of theta and can produce the following statement. Next, we recall the definitions of both involved trigonometric functions, and now we can draw the reference triangle with theta in standard position and label the sides appropriately. We then use the Pythagorean theorem to find the missing side, and finally plug in the needed sides into the expression in question. However, this argument only works when x is greater than 0, because the hypotenuse in the reference triangle must be positive. So what do we do when x is less than 0? If x is negative, then we make the hypotenuse positive by factoring out the negative sign and drawing the reference triangle in the second quadrant. After simplifying the trigonometric expression, we now have two formulas, one for positive x and one for negative x. However, this can be elegantly written as a single formula using the absolute value notation. In summary, we now have the formula for the derivative of the arcsecant of x function, as well as the formula for the antiderivative of its derivative. Now we can find the derivative of the following function. We start the process by recognizing that we have to find the derivative of a composition of the arcsecant function applied to the natural logarithm function, which is equal to the following expression, in which we know how to find all the components. And there isn't much to simplify here. Let's do another example. We start the process by recognizing that we have to find the derivative of a composition of the power function applied to the arcsecant of x, which is equal to the following expression, in which we know how to find all the components. And there isn't much to simplify here. Let's do an example of integration. We first recognize the pattern and rearrange the integrand. Then we set up the substitution by setting a new variable, let's say t, equal to arcsecant of x, and finding the differential of t. Next, we plug in everything into the original integral, and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function arcsecant back for t. Let's do another example. This time we'll do a linear substitution. We set up the linear substitution by setting t equal to 5x and finding the differential of t and expressing the x in terms of dt. As a result, we have a simple indefinite integral in terms of t. We continue with the integration process by finding the antiderivative and replacing t with the original function. We discussed how to differentiate and integrate the functions that have arcsecant of x as one of their components.